Bismillahirrahmanirrahim and Assalamu alaikum dear students. Welcome to our next lecture, and today we are continuing our previous topics, that is the parametric classification, and we look into the details that how the parametric classification is done with the help of statistical methods. We will also look at few examples in order to mature our concepts. Let us consider the data set given in our car sales.csv. I will provide you this data set along with these slides, so you can get this from the GitHub. We will apply the Bayesian theorem, which is given like this. We have already seen this Bayesian theorem previously in our last few lectures. Here theta is the class to be predicted, the parameter that we want to predict, right? And the parameter could be a class as well. Whether customer purchases a car or not, we want to determine this based on this data set. And from the data set we get P of theta, which is the prior probability. What is the probability that a customer purchases a car? We get the likelihood P theta given x, mean what is the likelihood, what is the likeliness that if we are given with this value, the theta, the class, the car would be purchased. And similarly we will get the third, which is the evidence also. Mainly we are concerned with these two quantities, right? And this is the data set that we will be working with. Total instances in our data set, the population are 400. Here few instances have been shown, which consist of the user ID, the gender, age, estimated salary, and whether he or she purchases a car or not. In our data set there are total 400 instances, and x we use a random variable which is used to denote the salary, which is more than 50,000 in our sample. And here is the data set which is given in the form of a CSV file, and you can see that it contains in total 401 instances, whereas the first one is the titles of the columns given over here. So there are in total 400 instances. Okay, and the probability of purchasing a car is 143, mean the probability where theta is 1, the parameter is 1, mean all those instances where the customer has purchased a car. So there are 143 instances in total. Next is the probability that a person with who has this is wrongly written over there, who has purchased a car has salary more than 50,000. So that is given like this: a person who has purchased a car, what is the probability that he has his salary more than 50,000? It's not equal to 50,000, it's more than 50,000. So we will be working somewhere with the CDF kind of thing. There are 99 instances, right? And the probability of persons with salary more than 50,000, that is given by this. There are 276 people who have the salary greater than 50,000. The probability that a person with salary higher than 50,000 will purchase a car. Now look at this, is the likelihood and this is the posterior. In likelihood we are going to see that what is the probability that a person who has purchased a car has salary more than 50,000. So we are looking at the probability of finding the people with 50,000 salary who have purchased the car. But here in the posterior it has been reversed. What is the probability that a person with this much salary would buy a car? And we write it like this, which is the Bayesian formula according to this, right? And after putting the values taken from the sample or the data set, we come up with this result, that there is 51% chance that a person with this much salary or the salary higher than this would purchase a car. And now by looking at the pack learning algorithm which we have seen in the previous lectures, where we were just trying to see that if the probability of new instance comes, if this is our true space where the probability it lies to our defined class, and if new comes near to it, right, if we divide this distance between the two parts 50-50% and it is more than 50%, so we will classify it as this person would purchase a car. If the probability is more than 50%, so we would say that the person who is being utilized, are simply saying any person who comes on the showroom and he tells that I have my salary which is greater than 50,000, so there is more probable chance that he will buy a car. So, this is a very simple calculation, and you are required to do the same working with the data set which have been provided to you, or even you can download different data sets from the internet and you can apply these kind of calculations on those to find whether the current person, whether the current instance is positive or negative. We have two classes, class 0 not going to purchase and class 1 mean that the person is going to purchase a car. So, where we can classify it, the probability is more than 50%. So, we can easily classify it among the people who will purchase a car. So, this is A who will not purchase a car, this is B who will purchase a car. So, this person could be classified here. Now, here is the exercise that you have to do yourself, and it would be better that you do on the paper pencil and then you program using Python or any other language that you are easy with and test it accordingly. Solve the above example for persons having the following salaries. Now, this is interesting. A person having salary 10,000, what is the chance that he would purchase a car or not? A person or the persons having salary greater than 80,000, the persons having salaries less than 100,000, and the persons having salary range 50,000 to 100,000. You have to work with the same data set that would be provided along with this lecture. Now, we look at the multi-classification using naive Bayes. Previously, we have seen a case of binary classification, and here we come with the multi-classification. Data set description. Let we have this data set, and this data set contains 4 values, 4 features and a class. I have simplified this and I have taken only one feature, which is sepal width, and I have excluded these 3 features, right, in order to make a simplified case for your easier and faster learning. So, we have the sepal width and the class. So, here you can see that 5 is the sepal width and this is the class of the flower. And now, we apply this Bayesian formula which we have already seen. We are going just to revise it, and here from this data set where we have only 12 instances, we can see that there are 3 classes: Iris setosa, Iris versicolor and Iris virginica. And by looking at the data set, we can see that different probabilities. For example, we can see I have divided the data set into 3 classes here. This is the same data set which have been divided. So, we have 3 classes, right, and for each class the probability is given as this: 3/12, 4/12 and 5/12. What is the probability of class 1, which is actually Iris setosa? So, that is 3/12. 12 are the total and 3 are the instances that belong to our class. And similarly, for class 2 it is 4/12, for class 3 it is 5/12. Remember, these are known as priors which we know from the data set. And now, we come to the likelihoods. Here you can see that the probability x is 4. Now, this is our x, the first feature, and this is our class our target, or we can denote it as, first it could be denoted with x, and other this could be denoted as y. So, probability of x, that is 4, given class theta 1. So, what is the probability that in one class or first class x would be 4, that is 2 by 3. Here you can see that there are 2 instances which have the value 4 out of these 3 instances. So, remember we are saying about theta 1. So, class 1, we know about the class 1 that there are 3 instances in total and 2 which belongs to here. So, we write it like this, 2 over 3. Similarly, we see that what is the probability that x is 4 in class 2, given class 2 or in class 2. So, that is 0 by 4. In this class there is no instance which contain the value 0, 4. And here what is the probability that if we take the class 3, x is 4. So, again there is no instance which is 4. So, we will say that it is 0 by 4. Okay. After that, we look at what is the probability that x is 5 if we talk about the class 1. So, in class 1 only one instance is 5. So, we will say that it is 1 by 3. In class 1 there are 3 instances in total and 1 is 5. What about in class 2? It is 1 again out of 4. So, we have 1 instance out of 4. So, we write 1 over 4. Similarly, probability x is 5 in class 3, that is again 1, no other instance with the value 4. So, we can write it as 1 by 4. Now, we look at the value 6. What is the probability that 6 lies in class 1? No instance has the value 6. So, it is 0 by 3. And what is the probability that x is 6 given class 2? So, in class 2 there are 2 instances which have the value 6. So, we have 2 over 4. There are total 4 instances in the class 6. And what is the probability of occurring x is equal to 6 in class 3? That is 4 out of 5. So, we write it 4 over 5. Similarly, we work out for the value 7. So, from here you must be very much clear about that what is x, the data, and what is y, the parameter that we want to estimate. In our case we want to estimate the class. So, class is a parameter and x is the data, and this data could be either one featured, single featured, or multi featured. For your understanding, I have made it single featured. However, in practical cases you would be working with multi feature data set. Now, we proceed for the further calculations. The Bayesian formula could be written like that, right? And we see that was the probability theta 1. I have taken all these values from the previous slide, all these values, priors and the likelihoods, and the evidence that could be considered in this form, because we are working with a multi classification problem. So, let me look at this. So, in this formula, first we are going to calculate this term, right, that summation which goes from 1 to 3. We have 3 classes, and what we do over here, p of x I, p of theta I. So, you can see that we have 4 values for x. What are those 4 values? 4, 5, 6 and 7, right. So, here we have rearranged and we have got all the 4 values for class 1. 2 by 3, x is equal to 4 given class 1, x is equal to 5 given class 1, x is equal to 6 given class 1, and so on. So, we write here 2 over 3, 1 over 3, 0 over 3, 0 over 3 multiplied 3 over 12, which is given by this probability of class 1, which is this. Similarly, we work out for the class 2, we get all these values and we multiply them with this value 4 over 12. So, this you can see here. And for the third and the last class, we also get this 5 over 12 which is probability of class 3 multiplied by all the values taken from here. So, I hope you must be able to understand that how this expression have been derived. And now, in the next 2 steps, we just simplify these expressions and the result comes up 1. Interestingly, if the result comes up 1, we can just ignore this term, and we have seen in previous lecture as well that this is just a normalizing factor, so we can ignore it, and our formula could be simplified with this. So, here you can see that we have got only the numerator, and the equation is taken, denominator has been ignored. What is the probability that a flower for sepal length 6 belongs to class 1, class 2, class 3? Now, we have just got another flower. We have worked out with the data set and we have calculated all the statistics. Now, someone has given us a new flower which has the sepal length as 6, and we want to classify it among all these 3 classes where it should be placed. So, we have 3 classes, class 1, class 2, class 3. We will be using this expression for class I. For example, for class 1, we can say that what is the probability x equal to 6 has been given us, what is the probability that it would lie in class 1. So, that could be written as this 0 over 3 multiply 3 over 12. Now, what is a 0 over 3? It is a likelihood, this thing, and what is 3 over 12? This thing prior. So, we multiply the likelihood and the prior to find out the posterior. 0 over 3, that has been, we are talking about the value 6 in class 1. So, this is instance. If we are given class 1, what is the probability of 6 lying in our class? That is 0 over 3. We have placed here 0 over 3 multiply 3 by 12, which is given here. Similarly, if we want to predict it about class 2, so we will perform the same. This is 2 over 4, 6 in class 2, we have this, and 4 over 12 which is taken from here, this. So, we multiply them and we find some value, here we find some value. Then we talk about the probability that if x is equal to 6 is given to us, what is the probability that it would lie in class 3. So, we will consider this, which is 4 over 5, and we multiply it with the 5 over 12 likelihood, and the prior we get 1 over 3. So, we calculate the probability of new instance in occurring every class in each class which we already have defined. It is a map estimate. Its map estimate is given by maximum A posterior. Remember that we have calculated the A posteriors. All these 3 values are the posteriors for each class, one for each class. So, we want to see which one is the maximum, that is 1 over 3. It means that our new flower which has a sepal length 6, it would be placed in class 3. Hence, value 6 belongs to class 3. So, this argmax tells x that we have to choose the maximum of these 3 values. So, we have practically seen that what is map estimate. Exercises. You are required to extend this working for multi-feature data set. Previously, we have worked with a one feature data set when we were doing the binary classification here. So, you are required to extend this to multi-feature data set, and take a breast cancer detection data set from this site, from this link, applied the studied theory on it. And what the theory? That is multi-classification and binary classification. So, you will look at the data set whether you can apply this binary or multi-classification, and you have to write a program for it. A good example is given here. on this link, right? Try to understand and apply it on your problem. It's a good code and it tells you that how you can build a classifier using naive Bayes. Now we proceed. Parameter classification. The discriminant function is given by this. Again, you can see that this is the function which contains the likelihood and the prior. And we just replace theta with C in order to indicate that we are going to predict a class if we are working with multiple classes. And we just write it like this. It is because we are taking the log because the multiplication is a compute intensive and time consuming problem. So we convert this problem into a summation problem which is faster and not that much compute intensive. Okay. Let's assume that the underlying distribution is Gaussian. Let's say that the distribution of classes is given in the form of Gaussian. They are taken from a normal distribution, and the formula of likelihood of normal distribution is given this, right? If we are given Ci, the class, so the normal distribution is given like this. Putting this value in above equation, we get this. We put this value in this green equation, right, and we get this. You are required to do it on the paper and see whether this equation and this equation is same, whether it is correct or not, right. And now we move to further simplify this equation. We take the log of both sides as we have taken on the previous slide, and here you can see that we put here 2 pi, this 2 pi which has the power 1 by 2, when it is taken above the division it becomes minus 1 by 2. This has the power 1, when it goes up it becomes sigma minus 1, and this remains as it is. So we have only simplified this term and we have reproduced this term as it is. And we know that if we take the log of E of x, that becomes x. So by using this equation, we apply the log inside this expression, log 2 pi minus 1 by 2. So minus 1 by 2 is taken before the log and it becomes log 2 pi minus, because minus 1 is taken over here and this minus is due to this minus 1, log sigma I, right, you can write here I as well, minus x minus mu, and this is taken by using this fact, and this has been reproduced as it is. So I hope that you are able to understand that how the equation from here to here has been converted. So what it says that we can very easily find the posterior for the normal distribution. We are going to work it out later on in next coming slides. Example, let A is a car company that sells K type of cars, and let customer choice is based on its yearly income, which is denoted by X. So the salary of the customer is our random variable, which we assume that it's a normal distribution. It is taken from the normal distribution, or it forms the normal distribution. Let probability of Ci of class Ci, which is a prior, is the portion of the customers who buy car Ci. Let the yearly income distribution is supposed to be normal, which I have said over on this line as well. And now we suppose that this the probability x Ci. What it mean? It means that if we are given some particular class, what is the probability of salary, right, probability distribution of salary, and this sign tells that it belongs to this, the probability of salary. If some particular class is given, that belongs to a normal distribution which has the mean mu I and the standard deviation or the variance sigma I square, right. So, this has been taken this. Probability that a customer who bought a car type I has income X. Actually, this X is basically written like this: probability X is equal to sum X given Ci. And if you are following my lecture, we have already seen in the previous slides, and I have given you as an exercise to work with it, right. On this slide, on this example, binary parametric classification, we have seen that how to calculate the values. Remember, this could be either greater than or less than or equal to, right. And here I gave you an exercise to solve a similar kind of problem. Okay. So, mu I is the mean income of the customers buying car Ci, and sigma I is the variance of the income of such customers. If PCI and PXCI is not known, it can be estimated from the sample. This is interesting, right. This is the thing that we are going to work without. We do not know about the prior probability in the population, we do not know about the likelihood in the population. However, we are given some sample, so we can estimate these two things using the sample mean and the sample standard deviation. And this we have seen in the previous lecture, that we can use these two parameters to estimate these two parameters. Let we have sample which is given as x is equal to xt rt, right. You can say that xt is the instance, single featured or multi featured instance. Just like previously we have seen the sepal length, that could be either only sepal length or sepal length plus sepal width plus petal length, petal width, and R is the class, R it is the y, right. And where R of t is equal to 1 if x of t is belongs to Ci, mean the instance of the salary for which we are going to work out, if it belongs to Ci, we will have 1, value 1. In other words, just we say that if we denote here salary and we denote here the class, right. So, salary for example 50,000 and he purchases a car, right. So, we write in our data set 1. Salary for example 60,000 and he purchases a car, we write in our data set 1. If the salary is 70,000 for example and he does not purchases a car, we write here 0, right. And there are k classes of the cars, there are k type cars, sports car, family car, office car, and so on. For normal distribution, the parameters are these. If we are working with the normal distribution, so we have only these two parameters to estimate. The parameter estimates are given as, now we change the equation little bit to incorporate this multi-class problem into this. The sample mean is given as, previously we did not had these in our formula, we just has n over here in the denominator. But now as we are working with the multi-class classification, so we will get the sample mean for each class. Remember, this I denotes for each class, right. And if we are going to get the sample mean for each class, so we will count for prior only those instances which have value 1 for that class. And similarly, we will have the sample variance formula, and we will use this and this with the same reason which we have given for the mean, right. And estimate for prior is given by this, right. How the estimate for the prior is given? It tells us that we will count all those instances which have value 1 for class I and total instances in our data set. For example, if there are 400 instances in our data set and there are 120 people who have bought a particular class I of cars, so we will have 120 over 400, right. So, it is very easy. If we are given with the sample, we can calculate R for that particular class, we have the value of X, we can calculate the M as well, and we can find the values of these parameters, right. It is a good exercise that if you find some data set, and for that data set you suppose that it is normally distributed, and find a sample mean and sample variance for a multi-class classification problem with the prior as well. So, you have to write a code to find out these values. It will help you to understand how the classifier is working. Now, we look at the previous equation which we have seen in few slides before. We had this formula for our normally distributed population, and now we use the same formula for our normally distributed sample, and that is this. The first term is a constant and can be dropped because it is common in for all classes. So, this formula is being used for I classes. For example, if we have 3 classes and we take the case of our flower example, where we have Setosa, Virginica and Iris. So, we have 3 classes. If we are going to find this discriminant function for each of 3 classes, this value would not change with the change of class. It is a constant. So, in every formula for class 1, for class 2 and for class 3, this would be included. So, we can just ignore it, it is a constant. If the priors are equal, the last term can also be dropped. Okay, it will have only effect if the prior are not equal, but let we suppose that prior for each class are equal, mean we have a balanced data set in which we have, for example, 50-50 instances, right. If you are working with this flower data set, so flower data set contains 50 instances for each class. So, in that case, this prior probability for each class would be 50 over 150. So, again it is a constant number and it is not going to affect the formula. So, we can also ignore it. If we can further assume that variances are equal, again we say that this is equal, log S1 is equal to log S2 is equal to log S3 and so on. So, if these are equal and we assume, so we can also neglect it. Then we are left with only this, and because these are equal, so we can also ignore it, we can consider it as 1. So, we are left as GIX is equal to minus into x minus mi square, right. And we will find, we are given a set, a flower with the, let us say that we are working a flower set with only one feature, which is a sepal width or sepal length, as before we are working. So, the value of x and the sample mean, we subtract it, and we also find means for each of 3 classes. For example, we find previously for class 1 M1, we find M2, we find M3, and we take the difference of x with each class, right. We take the difference and we get the modulus of it in order to remove the negative or the positive sign. So, this new instance, this x would be classified, would be given the class with which it has the minimum distance, that we write like this, right. We may have x minus m1, we may have x minus m2, we will have x minus m3. So for each of these three, the minimum value where it finds the minimum value, x is given that class. For example, x has the minimum value when it is subtracted with class m3, right. So we will say that x belongs to class 3, right. In this way, we can classify a data which is normally distributed, and I hope that you have understood all the concepts given in this slide. Now we come toward an exercise. Using Python and NumPy, you have to create a collection of 100 values which are normally distributed with mean 50,000 and standard deviation 10,000. There are 3 cars in your data set, 3 types of cars basically: Suzuki Mehran, V2 and Toyota Vitz. You have to randomly assign a car to a salaried person. The shape of the data set is as follows, and here interestingly you will keep a balanced data set, right. For example, there would be the same number of people buying Mehran, there would be same number of people buying V2, and there would be same number of people buying Toyota Vitz. Now using this 100 item set, you can increase it up to 150 as well. Just I say that, not 100, but it would be 150 with 50 examples of each car, right. We estimate the population distribution, right. Because we are saying that it's a normally distributed, so you will apply the formulas given in the previous slides and find the parameters of normal density using formulas. Here x is given as, now first you will use x as a single featured value, and then you will use x as a double featured value, right, as we have given over here. You will estimate this probability of x, m and s square, right. We are going to find the likelihood, not the posterior, right. So we will find m from the data set that we have generated, we will find s square, the variance of sample from the data set we have generated, and by looking at that we will find the likelihood that if some x is given, if these parameters are given, m and s, what is the probability that x, which consists of salary first and then salary and grade both, would be, what would be the probability, right. What would be the probability that he would be buying some particular car. So we will use this formula, right. Base formula is very simple formula in which we place the values taken from any distribution that could be uniform, that could be Poisson, that could be standard normal, or normal distribution, or Gaussian, or whatever it is, right. The formulas are given here. You are required to write the program to implement these formulas and get the statistics and the predictions as given in this exercise. Now we look at an example. For 2 classes, the midpoint between 2 means is a threshold of dissonance. If we are working with the 2 classes, for example, we have g1x and g2x. So we will have for g1x x minus m1 square, and for g2x we will have x minus m2 square. That has been taken from here, right. We have derived this formula, so we are using this formula in that slide. And if we, here we have taken the squares out, right, this is now equal to this, and we can simplify it like this, x minus m1 and x minus m2, right. So we can simplify it like this, and finally it could be written as this, x is equal to m1 plus m2 over 2. So this is the decision boundary about x, right? For two classes, the midpoint between the two means is the threshold decision, right? Let's say that this is C1 and this is C2, posteriors with equal priors. These are the likelihoods. So this is the decision boundary for our posteriors, right? Here you can see that this is the formula of likelihood and this is the formula of posterior. A likelihood function, we draw here the likelihood function of both G1 and G2, and then B the posteriors with equal priors for two classes when the input is one dimensional. Okay, so these values are one dimensional input. For example, we say that x is the salary. Variances are equal and the posteriors intersect at one point, which is a threshold of decision. So this is the threshold of decision, and if the value of x comes below this threshold decision, so we put it into the class C1. If that comes above than this value, we put it into class C2, and we find the value of x using this formula. Okay, so you can easily implement it in Python. You are required for your own exercise to implement it, right, using the same car data set that we have generated in previous example, in this exercise. Another example, when the variances are different, there are two thresholds which can be calculated easily. Remember that previously we have assumed that the variances are same, right? In this slide we assumed that the variances are same. However, if they are different, then what would be the behavior of our classifier? When the variances are different, there are two thresholds which can be calculated. Here this is the likelihood function, probability x given C1 Ci basically. So we can draw it if we have two classes. So for two classes we draw it like this, for second class we draw it like this. So this is C1 class and this is C2 class, and here remember, here you can see that the variances are same, right, but here the variances are different. This dotted line distribution has higher variance as compared to this C1 variance. So posterior with equal priors, if we assume that the priors are equal, the probability in the data set, the instances in the data set are same, 50-50 for example, then if we draw the posterior, right, that would be like this. This is the posterior of class C2 and this is the posterior of class C1, right, and if the priors are different, this has the effect of moving the threshold of decision towards the mean of the less likely class. We discuss this point later on, but however here we can see that the posteriors with equal priors have this kind of two thresholds, right, and if we use the formula like this previously, m1 plus m2 divided by 2. So if the value of x lies in this region, we give this class to x. If the value of x lies in this region, we class C2 to our x. However, if it lies in this class, then we give class C1, because here you see that C2 is higher than C1 and here C1 is higher than C2, right, and in this section again C2 is higher, so we will assign a class C2, right. If the priors are different, this has the effect of moving the threshold of decision towards the mean of less likely class, right. These are the expected risks. This shows that the thresholds of the decision toward the mean that if the priors are different, so this value could be like this, right. It means that we will have more space of error, we would have more chance of error, right. That's why whenever we are working with the data sets, we try our best to keep that data set in a balanced form. Balanced form means that the number of instances of each class should be equal as maximum as possible. That's all about for today. I hope you are able to understand the concepts given in this lecture. You are very required to do the exercises which are given in this lecture. Try to understand the formulas, try to understand the programming which is required to code those formulas and their effects. Try to draw the variances and the means and their distributions, right, by changing different values in the data set, the number of parameters, and see their effect. See you next time in next lecture. Allah Hafiz.